The American Petroleum Institute and Howell Training present Catalytic Reforming. Refining processes have historically been developed to meet the ever-increasing demands for gasoline. These demands have brought about many changes in refinery operations, as well as the development of entirely new processes. Processes like fluid catalytic cracking and alkylation were developed during World War II to increase the production of motor and aviation gasolines. After the war, a need developed for higher octane gasolines, which could meet the requirements of automobiles with high compression engines. One way to enhance the octane number was to add tetraethyl or tetramethyl lead to the gasoline. In the 1970s, however, the Environmental Protection Agency ordered a gradual phase down of the lead content in gasoline. Fortunately, another method had already been introduced that could improve the octane rating of gasoline. This method, called catalytic reforming, uses a series of chemical reactions to create high-octane gasoline blending components. To understand how catalytic reforming works, you need to know a little about the chemistry of crude oil. Crude oil is composed of hydrogen and carbon atoms that have bonded together to form molecules called hydrocarbons. Hydrocarbons are formed in a variety of different shapes and sizes. They range from small, simple molecules to large, complex compounds. The characteristics of a particular hydrocarbon, such as its boiling point, flash point, and color, are determined by the size and structure of the molecule. It is these characteristics that determine what types of products various hydrocarbons can be used in. Basically, hydrocarbons can be grouped into four major series or classes according to the way they are structured. These are the paraffins, olefins, naphthenes, and aromatics. The hydrocarbons within each class have bonded together in a similar manner and have many of the same characteristics. In terms of gasoline blending, the characteristic we are most concerned with is octane number, and the highest octane numbers are found in the aromatic class of hydrocarbons. This brings us back to the purpose of catalytic reforming, which is to convert paraffins and naphthenes into high-octane aromatic compounds. But how is this accomplished? Catalytic reforming uses heat, pressure, and a catalyst to rearrange or reform the structure of hydrocarbon molecules. The feed to a catalytic reformer is usually a low-octane naphtha. The feed is primarily composed of paraffins and naphthenes, which explains the low-octane rating. Reforming occurs inside a series of reactors where the feed is contacted with the catalyst. The catalyst promotes several chemical reactions which reform paraffins and naphthenes into high-octane aromatic compounds. The produced by catalytic reforming is called reformate. Reformate may be used as a petrochemical feedstock or as a gasoline blending component. Secondary reforming products include hydrogen, along with some light hydrocarbons. In the next segment of the program, we'll take a closer look at the reformer equipment. But first, you need to know more about the characteristics of different hydrocarbons and how they react during the reforming process. Stop the tape and turn to Workbook Period 1. Segment of the program, we'll take a look at the equipment that makes up a catalytic reforming unit and discuss what happens to the feed as it passes through each section of the reformer. The feed is usually given some type of pre-treatment prior to entering the reformer. In most refineries, this means sending the naphtha through a process called hydrotreating or desulfurization. Hydrotreating removes contaminants in the feed, such as sulfur, lead, arsenic, and nitrogen. These impurities must be taken out of the feed, or they will be deposited on the reforming catalyst and damage it. When the naphtha is free of contaminants, it is ready to be reformed. The equipment in a typical reformer consists of 3 or more reactors, a furnace, a separator, a stabilizer, and a recycle compressor. The first step in reforming is to mix the feed with a hydrogen-rich gas, and then heat this mixture in a furnace to around 900 to 950 degrees Fahrenheit. This temperature is sufficient to totally vaporize the feed and allows the desired reactions to take place. Next, the vaporized feed and hydrogen are charged to a reactor where they come into contact with the catalyst. The catalyst promotes several chemical reactions which rearrange or reform the structure of the hydrocarbon molecules. In most reforming units, the feed must be processed through 3 or more reactors to obtain the desired product. The naphtha is further reformed as it passes through each reactor. The product of one reactor is always reheated in a furnace prior to entering the next reactor. This is because the net effect of the reforming reactions is endothermic, meaning that heat is absorbed. So reheating is necessary to keep the reactors operating at the proper temperature. The product from the last reactor is cooled and liquefied, and then sent to a separator. The product is condensed so that it can easily be removed from the hydrogen that is produced by the reforming reactions. Much of this hydrogen is recycled and mixed with fresh reactor feed. This is done to maintain a high concentration of hydrogen in the reactors. The amount of hydrogen in the reactors must be kept above a certain level, or the catalyst will be damaged. The liquid product from the separator is sent to a stabilizer. The purpose of stabilization is to separate out light hydrocarbon gases that were created by the reforming reactions. The product drawn from the bottom of this vessel is the stabilized reformate. During the reforming process, coke, or carbon, is gradually deposited on the catalyst. As this happens, the catalyst's ability to reform the feed declines, so eventually the coke must be removed. The catalyst is cleaned or regenerated by burning the coke off its surface. Reforming units are often classified by the method they use to regenerate the catalyst. Basically, there are 3 different ways to do this. The first type of unit is called a semi-regenerative reformer. With this type of reformer, the reactors run several months or more between regenerations. When the catalyst needs cleaning, the entire unit is taken off stream so that all of the catalyst can be regenerated at the same time. The main disadvantage of this method is that a complete shutdown is required to clean the catalyst. Some units are equipped with a swing reactor so that part of the catalyst in the system can be regenerated while the other 3 reactors are in operation. This is called a cyclic reformer. Because the catalyst is cleaned in cycles, it is not necessary to shut down the unit for regeneration. A third way to regenerate the catalyst is with a continuous reformer. With this method, a portion of the catalyst is continuously removed to a separate regenerator, where it is cleaned and then returned to the system. Catalyst regeneration usually involves more than just burning off the coke. The catalyst is usually treated with chemicals to help restore it to its original activity. This treatment will vary depending on the type of catalyst that is being used. Let's take a closer look at how the catalyst is regenerated and how the reforming equipment works. Stop the tape and turn to Workbook Period 2. In this part of the program, we'll take a look at some of the major operating conditions or variables that must be controlled during the catalytic reforming process. We'll also discuss how these variables affect product yields and quality. Normally, a reformer is operated to produce the maximum amount of reformate that meets a specified octane number. This chart shows the relationship that exists between octane number and yields. You can see that as the octane number goes up, the volume of reformate produced goes down. So the higher the octane specifications, the less reformate we are able to produce. This means that if the unit is producing reformate that is above octane specifications, product is being needlessly wasted. Let's move on to some specific operating variables and consider how they affect reformate yields and octane number. Since heat is required to drive the reforming reactions, it follows that temperature in the reactors is a key operating variable. The desired reactor temperatures are maintained by passing the feed through a furnace prior to each reactor. Normally, these temperatures are kept at a set value unless the octane number of the reformate decreases. If the octane number starts falling off, it can be raised back to the desired value by increasing the reactor temperatures. A 3 to 5 degree increase will usually raise the octane number by about 1. As the catalyst deactivates during the course of a run, the octane number of the reformate will often fall below specifications. When this occurs, the reactor temperatures can be increased to bring the octane rating back to the desired value. There is, of course, a temperature limit above which the reactors should never be operated. The pressure in the reformer is another important operating variable. This pressure is controlled by regulating the amount of hydrogen that is allowed to leave the system. In most instances, pressure is maintained at a fairly constant value throughout the system. If the pressure increases, more light hydrocarbons are produced in return for less hydrogen and reformate. A pressure decrease results in greater hydrogen and reformate yields, but causes more coke to be deposited on the catalyst. The system pressure is generally not adjusted to change product yields or quality. The feed or charge rate to the reactors is a third operating variable. Normally, a constant amount of feed is charged to the reactors at all times, but feed availability problems or mechanical difficulties may occasionally force a feed rate reduction. If the feed rate decreases, the system will be thrown out of balance unless other operating variables are adjusted. When less feed is being processed, the reformate octane number can be reached at a lower temperature, so the reactor temperatures should be reduced until the feed rate returns to normal. The composition of the feed also affects product yields and quality. For example, if the feed contains too many heavy, high boiling point hydrocarbons, coke production will increase at the expense of reformate yields and octane number. Another important operating variable is the hydrogen recycle ratio. This is simply a measure of the amount of hydrogen in the recycle gas compared to the amount of hydrocarbons being charged to the unit. Recall that hydrogen must be mixed with the feed to minimize coke laydown on the catalyst. If the hydrogen recycle ratio is not kept above a minimum value, coke deposits may force an early shutdown for catalyst regeneration. There are several situations, such as a lower concentration of hydrogen in the recycle gas or a reduced compressor capacity, that can cause the hydrogen recycle ratio to decline. To promote the desired reforming reactions, the catalyst must be active. There are several variables that affect the catalyst activity. You have already learned that coke deactivates the catalyst, reducing product yields and quality. Another variable that affects the catalyst activity is the chloride level on the catalyst. In order for the catalyst to remain active, a certain level of chlorides must be maintained on its surface. This level can be adjusted by injecting chlorides into the feed or the recycled gas streams. A small amount of water is sometimes injected into the feed or recycled gas streams to spread the chlorides across the catalyst. Water injection rates must be carefully monitored to ensure that the chlorides are properly dispersed. Chlorides and water are often injected at the same time to keep these two variables in balance. The vapor pressure of the reformate product must also be controlled during the reforming process. Vapor pressure is a measure of a liquid's tendency to vaporize at a given temperature. Light hydrocarbons, like propane, have a high vapor pressure because they vaporize readily at normal temperatures. We usually try to keep the vapor pressure of the reformate low enough so that it will stay in a liquid state under average climatic conditions. The vapor pressure of the reformate is controlled in the stabilizer. Prior to stabilization, the reformate vapor pressure may be several hundred psi or higher. Stabilization removes light hydrocarbons from the reformate, which reduces the vapor pressure to around 5 psi. In addition to the variables we've considered so far, there are many other temperatures, pressures, levels, and flows that must be monitored and controlled throughout a reformer unit. The unit foreman or supervisor is usually responsible for setting the value of these process variables. The operator's job is to make sure they stay within their allowable tolerances. A sudden change in the condition of a process variable often indicates there is a problem somewhere in the system. Let's review some of the major operating variables in the catalytic reforming process and take a closer look at how these conditions are monitored and controlled. Stop the tape and turn to Workbook Period 3. The program will deal with the operator's duties on a reformer unit. An operator is usually responsible for sampling and testing various process streams, adjusting the unit operating variables, making daily inspections, keeping the unit log, and responding to abnormal operating conditions. Let's start with sampling and testing. An operator will be required to draw samples from the feedstock, reformate product, and recycled gas streams. Tests are then run by the operator or a lab chemist to determine the composition of the samples. The reformer feed is often given a doctor test to check for sulfur. In the doctor test, a sample of the feed is mixed with a chemical that reacts with sulfur. If the sample turns black, this is an indication of sulfur. It is important to detect sulfur in the feed because it can quickly deactivate the reforming catalyst. Another test performed on the feed is the ASTM distillation test. This test identifies what types of hydrocarbons are in the feed by their respective boiling points. Hydrocarbons that boil above 400 degrees Fahrenheit should be kept out of the reformer because this heavy material will coke up the catalyst. The composition of the recycled gas can be determined with a gas analyzer or by mixing a sample of the gas with special chemicals in what is called a Draeger tube. These tests identify contaminants like hydrogen sulfide that should have been removed by desulfurization. They can also determine the hydrogen chloride levels and the hydrogen purity in the recycled gas. A moisture analyzer is often used to check for water in the feed and in the recycled gas stream. A precise amount of water must be kept in the system to spread the chlorides across the catalyst and keep it active. Several different tests are run daily on the reformate product. Tests for octane number and vapor pressure are performed by a lab chemist to make sure the product demands for gasoline. These demands have brought about many changes in refinery operations, as well as the development of entirely new processes. Processes like fluid catalytic cracking and alkylation were developed during World War II to increase the production of motor and aviation gasolines. After the war, a need developed for higher octane gasolines, which could meet the requirements of automobiles with high compression engines. One way to enhance the octane number was to add tetraethyl or tetramethyl lead to the gasoline. In the 1970s, however, the Environmental Protection Agency ordered a gradual phase down of the lead content in gasoline. Fortunately, another method had already been introduced that could improve the octane rating of gasoline. This method, called catalytic reforming, uses a series of chemical reactions to create high-octane gasoline blending components. To understand how catalytic reforming works, you need to know a little about the chemistry of crude oil. Crude oil is composed of hydrogen and carbon atoms that have bonded together to form molecules called hydrocarbons. Hydrocarbons are formed in a variety of different shapes and sizes. They range from small, simple molecules to large, complex compounds. The characteristics of a particular hydrocarbon, such as its boiling point, flash point, and color, are determined by the size and structure of the molecule. It is these characteristics that determine what types of products various hydrocarbons can be used in. Basically, hydrocarbons can be grouped into 4 major series or classes according to the way they are structured. These are the paraffins, olefins, naphthenes, and aromatics. The hydrocarbons within each class have bonded together in a similar manner and have many of the same characteristics. In terms of gasoline blending, the characteristic we are most concerned with is octane number, and the highest octane numbers are found in the aromatic class of hydrocarbons. This brings us back to the purpose of catalytic reforming, which is to convert paraffins and naphthenes into high-octane aromatic compounds. But how is this accomplished? Catalytic reforming uses heat, pressure, and a catalyst to rearrange or reform the structure of hydrocarbon molecules. The feed to a catalytic reformer is usually a low-octane naphtha. The feed is primarily composed of paraffins and naphthenes, which explains the low-octane rating. Reforming occurs inside a series of reactors where the feed is contacted with the catalyst. The catalyst promotes several chemical reactions which reform paraffins and naphthenes into high-octane aromatic compounds. The produced by catalytic reforming is called reformate. Reformate may be used as a petrochemical feedstock or as a gasoline blending component. Secondary reforming products include hydrogen, along with some light hydrocarbons. In the next segment of the program, we'll take a closer look at the reformer equipment. But first, you need to know more about the characteristics of different hydrocarbons and how they react during the reforming process. Stop the tape and turn to Workbook Period 1. Segment of the program, we'll take a look at the equipment that makes up a catalytic reforming unit and discuss what happens to the feed as it passes through each section of the reformer. The feed is usually given some type of pre-treatment prior to entering the reformer. In most refineries, this means sending